Ever wonder how AI gets so smart? A huge part of the answer is data. But what happens if you just don't have enough? Well, that's what we're talking about today. It's a game-changing technique called data augmentation, and it's all about making more from less. Let's dive in.
All right, first things first, you gotta understand something crucial about modern AI. These machine learning models, they are insanely hungry. I mean, they need to just gorge themselves on massive amounts of data to learn how to do their jobs right. Whether that's spotting a cat in the picture or figuring out tomorrow's weather.
Okay, so what happens when the well runs dry? When you just run out of data. Or maybe even worse, what if the data you do have is all lopsided? This is a massive problem. It can lead to AI that's not just wrong, but frankly, dangerously unreliable. And listen, it's not just about having a ton of data. You could have a data set the size of a mountain, and it could still be totally broken. If it's imbalanced, and what I mean by that is, you've got loads of examples of one thing, but only a tiny handful of another, well, you are heading straight for a biased model. No question about it. Just look at this medical data set to see what I mean. We've got 90 samples from healthy patients, but only 10 from patients who have a certain disease. Now, if you train an AI on this, what's it going to learn? It's going to learn the lazy way out. It'll just guess healthy every single time, and hey, it'll be right 90% of the time. But it would completely fail at its most important job, actually finding the disease. That's bias in action, and in a case like this, it could be literally life or death.
So, how in the world do we fix this? Well, this is where our hero, data augmentation, swoops in. It's this really clever strategy for basically creating more data from the stuff you already have. And it works on everything from pictures you can see to signals you can't.
So here's the big idea in a nutshell. Data augmentation creates new, sort of synthetic data points by just making these tiny, realistic tweaks to the data you already have. This blows up the size of your training set, which helps the model learn way better and stops it from getting obsessed with the weird little details in a small data set. That's a classic problem we call overfitting. Okay, let's circle back to that medical data set, that crazy 90-10 imbalance. How do we fix that? Well, one of the go-to methods is an algorithm with, I gotta say, a pretty great name, SMOTE. That stands for Synthetic Minority Oversampling Technique. So how does this SMOTE thing actually work? It's pretty cool, actually. First, it looks at the minority class, in our case, the 10 patients with the disease, and it just picks one. Simple enough. Then it finds its closest neighbors, the other diseased data points nearby. And for the final step, the magic happens. It creates a brand new, totally synthetic data point somewhere on a line between the original point and its neighbor. You just do that over and over, and suddenly, you've got a bunch of new diseased samples. Your data set is balanced, and the AI has a real fighting chance to learn properly.
Okay, so we've seen how this works for balancing out numbers in a dataset. But let's get visual. We're going to talk about the place you see data augmentation the most, computer vision. This is the whole shebang of teaching computers how to see and understand the world like we do.
And, this isn't some brand new idea. People were doing basic versions of this way back in the mid-90s to train the very first convolutional neural networks. But then the 2010s hit, and those networks got insanely powerful. Suddenly, data augmentation wasn't just a neat trick anymore. It became an absolutely critical, can't-live-without-it tool for anyone working in image recognition.
When we're talking about images, the techniques usually fall into three big buckets. First, you've got geometric transformations. That's all about changing the position or angle. Then there's color space transformations. Think lighting and color. And finally, you have noise injection, which is basically adding a little bit of real-world messiness.
All right, let's kick off with geometric transformations. The whole point here is to teach the AI a really important lesson. An object is still the same object, no matter how it's turned, where it is in the frame, or how big it is. This is absolutely fundamental for recognizing things out in the wild. I mean, check out these examples. It's super intuitive. You take one picture of a cat, right? You can rotate it a little, flip it horizontally, shift it over to the side, or even crop and zoom in. Every single one of those simple moves gives you a brand new training image, and it all helps the AI understand that a cat can look like, well, all of these things.
Okay, next up, color. Because let's be real, the world isn't a perfect photo studio, right? Lighting changes constantly. Colors can look faded or they can be super intense. So color space transformations help the AI handle all that. We're basically training it on images that fake all these different lighting situations. So how do we get our AI ready for that? It's simple, really. We can take one photo and make a version that's brighter, another that's darker. We can crank up the contrast to make the edges pop, or mess with the color saturation. There's even a technique called color jittering that just randomly messes with all these things at once. The result? A much tougher AI that won't get confused by something as simple as a camera flash or a gloomy, overcast day. But here's where it gets really interesting. Augmentation isn't just for pictures. It is incredibly powerful for analyzing data you can't even see, things like biological signals and mechanical vibrations. And honestly, this is where the technique is really pushing the boundaries. Think about it. Images are all about pixels arranged in space. But signals? They're about waves and frequencies that change over time. You know, like a brainwave picked up by an EEG, or the hum and vibration from a car engine. The data looks totally different, right? But the fundamental problem is exactly the same. You almost never have enough of it, especially when you're looking for something rare, like a specific problem or an anomaly. This is a huge deal in medicine, where good data can be super rare and difficult to get. For example, researchers have used augmentation to create synthetic muscle signals, that's EMG signals, to get a better handle on Parkinson's disease. In another case, people have augmented EEG brainwave data to build systems that are way more accurate at recognizing human emotions. I mean, this is seriously cutting-edge stuff. And it's not just in medicine. The very same ideas are being used to cook up synthetic mechanical signals. This is driving innovation in, well, everything. We're talking robotics, 5G communications, even forecasting wind speeds for our renewable energy grids. Okay, so we've covered what data augmentation is, the mechanics of how it works, and seen all the different places it's being used. So let's get down to brass tacks. What's the bottom line? What are the actual measurable results we get from using this stuff? I love this quote from the research because it really hits on a key point. You don't always need some ridiculously complicated solution. A lot of these really powerful augmentation methods, we're talking simple stuff like flipping an image or adding a little bit of noise. They are so simple, but the impact they have is just massive. And we can actually put a number on that massive impact. One study, which was all about recognizing hand gestures from muscle signals, found that just by using augmented data, they boosted performance by up to 16%. That is a huge jump in accuracy, and all it took was making the data smarter, not just bigger. So, if you take away one thing from all this, let it be this. Data augmentation isn't just some clever little hack. It's a core strategy for building AI that is stronger, more accurate, and just plain more reliable. At the end of the day, it's about building better AI by first creating better data. So we figured out how to create synthetic data to help AI make sense of the world we live in now. But it leaves you with a pretty wild thought, right? What if we could create entire synthetic realities to train AI for problems and challenges that don't even exist yet? The possibilities are just staggering, and it all starts with this simple, powerful idea of data augmentation.